We have to determine which of these sentences is statement. First, what is statement? Statement is declarative sentence that is either true or false, but not both true and false. So let's read first example. We have a good day. What we can say about the sentence? We don't know if it's true or not. It's just comment. So this is not statement. We have 210 as even number. If you don't know definition of even number, you don't know it is even number or it is not even number. But the sentence is either true or is false and is not both true and false. So it is statement. Do you like shopping? This is question, so this is not statement. We have x squared plus 1 is greater than 0. We have x to second power, so this gives us always positive or equal 0 number. Plus 1, so on the left side we will always have positive number. So positive number is greater than 0. So this sentence is true. So this is statement. Next example, we have Berlin is in Europe. Berlin is the capital of Germany. So we know that Germany is in Europe. So this is true sentence. So this is statement. And we have sentence today is Monday. The true or false this sentence will depend on which day you will do this example. For me, I have today Tuesday, so this sentence is false. But we always can say that this is false or true. So this is statement. This is my solution. Determine the simple statements in each compound statement. We know that the statement is a declarative sentence that is either true or false, but not both true and false. Next, a simple sentence is a statement that conveys a single idea. What is compound statement? Compound statement is a statement that conveys two or more ideas. We know that we connect simple statements with words and phrases such as and, or, if, something, then, and, if, and, only if. Creates a compound statement. George Bull used symbols such as P, Q, R, S, and so on to represent simple statements, and we used symbols like for and we use symbol conjunction. This is symbol for or, this is operator for disjunction. If and something, then we will use symbol. Sometimes we have one line, sometimes double. It depends of book. And if and only if is the same situation. Sometimes we have in book one line on both sides arrows, or we have doubles line with arrows on both sides. And for simple sentence we use P, Q, R, S. Let's read first example. We have if it's raining, then there are clouds in the sky. We have phrase if and then. What else? It is raining is simple statement. We can say that it is true or not. So let's put that this is our first symbol statement. And next we have there are clouds in the sky. We can say always it is true or not. So this is statement 2. Simple idea. This is our next simple statement. So we have in first example 2 simple statements. First, it is raining, and the second is there are clouds in the sky. Next example, we have I swim if and only if the water is not warm. In this example, we have phrase if and only if. This phrase collects 2 simple statements. First is I swim. This is true or not. So this is simple statement. Let's put that this is our P. And the second we have the water is not warm. We can always say that this is true or not. So this is our second simple statement. I just put that this is Q. Okay, next example. Michael is driver and he is poor. We have connecting word and. And first sentence, Michael is drive is sentence because it's true or not, we can say. So this is our first simple statement. I can write this is our P. And we can always say that it is true or not if we know Michael, of course. And he is poor. This is next simple statement because has single idea. This is our Q simple statement. So we have in the third example, first simple statement is Michael is driver, and the second he is poor. And the last example we have 6 is an odd number or 6 is an even number. We have connecting word or. First we have 6 is an odd number. We can say that it is true or not. So this is simple statement because has single idea. Let's put that this is our P. And next we have 6 is an even number. Again, we can say that this is true or not if you know definition of even number or odd number. But you can always check this if you don't remember. And 6 is an even number is another simple statement because contains single idea. This is our Q simple statement. So in the last example, first simple statement is 6 is an odd number and second is 6 is an even number. So this is my solution. We have to write each symbolic statement in words. And we have given that P is for statement he is a poet. Q is for statement he is poor. R is for statement he will earn money. S is for statement he has talent. And T is for statement he will succeed. In the first example, we have P and this symbol represent conjunction and is for word and. This symbol is for word not. Let's put this like this. So we have first P statement is he is a poet. So we have next we have conjunction symbol. So this is for word and. Next we have symbol not. So we have to change our R statement to negative. We have he will earn money. Not, we have before are, so we will have he will not earn money. Next example, we have T, and this symbol represents biconditional statement. So we have T as he will succeed, and for biconditional statement, connective words are if and only if. So we have, for this symbol, we have words if and only if. So first we have to copy T statement. T is he will succeed. And next, because we have biconditional statement, so next we have to put if and only if. And we have are statement. Are is he will earn money. In the next example, we have conditional statement. Because we have this arrow, it means that we have to use connective words. If something, then, let me write this, when we have this arrow, we have to use word if, then, what else? We have in parentheses S and not Q. So when we have parentheses, it means we have to keep this sentence S and not Q together. So to separate statement which has to be together, we use comma. So we can start to write our statement. We have first not P. So P is he is a poet. Negation of P will be he is not a poet. So let's start because we have here implication if then. So we have to use if he is not a poet, is not a poet, comma, because we have these two statements in parentheses, so we have to put comma, then, and first we have S. S is for statement he has talent. So we have he has talent. Next we have conjunctions, so we have to use word and we have negation of Q. Negation of Q. Q is he is poor. So negation will be he is not poor, or we can write that he is rich. So let's put then we have if he is not a poet, then he has talent and he is not poor. Done. So this is our third example. And the last, we have biconditional statement because we have this symbol, and this symbol, like we said before, little earlier, that this is for words if and only if. And because we have parentheses, we have to keep these two statements together. So we have T first. T represents statement he will succeed. So we have he will succeed. Next, because we have these two statements in parentheses, so we have to keep them together. So I have to put now comma. Next we have if and only if. And in parentheses we have disjunction. For this symbol we use word or. So we have first statement not P. So we have to negate P statement. He is a poet. So not P will be he is not a poet. And now we have or. And we have statement S. S is for he has talent. So we got he will succeed if and only if he is not a poet or he has talent. So this is my solution. We have to rewrite each sentence in symbolic form. P is for Adele is a singer. Q represents Adele is a cook. R represents Adele plays the piano. And S is for Adele is rock star. First example we have Adele is a singer or a cook. And she is not rock star. We have to remember when we have comma, the statements on the same side of comma are grouped together. So we have to put together Adele is a singer or a cook. We have word or represent disjunction. For or word we use symbol this. So we have Adele is singer. This statement represents our P. So we have P. Next we have or Adele is cook. Cook. So we have Q. And next we have she is not rock star. S represents Adele is a rock star. So we have negation of S. So now we have to put this together. We have P or Q, and because we have comma, so we have to keep this two sentences together. Next we have and represents conjunction, and we use symbol like this. So we have and she's not rock star, so we have negation of S. Next example, Adele is not a rock star and she's not a singer or cook. We have to remember again when we have comma separates statements which have to be kept together. So this whole expression, because we have here word or, we have to this put in parentheses. And on the left side, first we have Adele is not rock star. S is for Adele is rock star. So we have negation of S. This is negation of S. Next we have she's not a singer. So we have negation of P, because P represents Adele is a singer. So we have negation of P. And we have or a cook. A cook is Q. And now we can rewrite our sentence to symbolic form. We have negation of S. Next we have and, so we have symbol, and next in parentheses, because we have comma, we have to keep this together. We have negation of P or Q. So this is solution to the second example. And next we have it is not true that, and next we have Adele is a cook or a rock star. Because we have comma, it means we have to keep this whole sentence together. And what else? Because we have it is not true. So we have negation of this whole sentence. So we have to put at the beginning symbol of negation. And in parentheses, what we will have? Adele is a cook. Adele is a cook is represented by Q. And rock star is our S. And for or, we use symbol of disjunction. So we have, this is our or. So we have Q or S. Not, and in parentheses we have Q or S. We have negation of disjunction. So next example, we have if Adele plays the piano, then she is a singer and she is not a rock star. At the beginning we have word if. It means we will have here conditional statement. In another word, implication. For implication conditional statement, we use symbol this. Or sometimes we have doubles line. And next we have here comma. It means we have to keep expression which is on the right side of comma together and on the left side of comma together. We have if Adele plays the piano. Adele plays the piano is our R. So this whole statement is represented by R. Next we have she is a singer. Singer is our P. This whole statement represents P. And she is not a rock star. Adele is a rock star is our S. We have not a rock star, so we have negation of S. So we have if and we have R. Then represent symbol this arrow, and because we have comma here, so now you put in parentheses this whole statement. We have she is a singer, so we have P, and she's not rock star, so we have negation of S. This is solution to our third example. And the last we have Adele is a singer if and only if she is not a cook and she is a rock star. Again we have comma. It means we have to keep together whatever is on the right side of comma and on the left side of comma. On the left side we have only Adele is singer. Singer, so this represents our P. So this is our P. Next we have if and only if, so we have biconditional statement here. We will use this symbol. We can use one line and arrows of both sides, or we can use double lines. So next we have she is not a cook. Because she is a cook is our Q. We have she is not a cook, so we have negation of Q. And next we have she is a rock star, so this is our S. S represents she's a rock star. So now we can rewrite our sentence, and we have P if and only if, and in parentheses we have negation of Q and represents conjunction, and we use symbol for and this S. So this is my solution. We have to decide if our statement is true or false. We have here compound statement because our statement has two single statements. First is 6 equals 3 plus 3. This is our first single statement because it has single idea. We can write that this is our P. And next simple statement is 8 is less than square root of 69. This is our second simple statement because it has single idea. This is our Q. And these two statements are put together and we have word and represent conjunction. And we use for conjunction symbol this. So we have P and Q. Because we have here conjunction statement and we know that conjunction statement is true only when both statements are true. So P must be true and Q must be true to be true this whole statement. So P represents 6 equals 3 plus 3. So P is true, of course. And we have Q is 8 is less than square root of 69. Square root of 69 is approximately 8.3. So 8 is less than 8.3. So Q statement is true. Because both statements are true, so our conjunction P and Q is true. This is my solution. We have given statement and we have to decide that this is true or false. We have and, so this is compound statement. This is conjunction because we have word and word and represents symbol this, and this is for conjunction statement. And what else? First we have to separate our simple statement. First statement, simple statement is 6 is different than 3 plus 3. Let's put that this is our P. And next we have 8 is less than square root of 69. Square root of 69 we have. So this is our Q, the second simple statement, because contains single idea. So we have conjunction here, P and Q. To find that this is true or false, first we have to check our first statement, P. We have 6 is different than 3 plus 3. 3 plus 3 is 6. So 6 is different than 6. No, it's not true. So P is false. Next, we have Q. Q is 8 is less than square root of 69. Square root of 69 is approximately 8.3. So 8 is less than 8.3, so this is true. we have conjunction here. Conjunction is true only when both statements are true. Because one is false, it doesn't matter which, so this conjunction is false. This is my solution. We have implication here because we have the symbol. The symbol is for statement. If something, then this is implication statement. We have to first determine simple statement. This is our first simple statement. 6 equals 3 plus 3. This will be our P. And we have 8 is less than square root of 69. This is our Q. So we have implication. P implies Q. P is our hypothesis and Q is our conclusion. Implication is false only when P is true and Q is false. So let's check our P. P is 6 equals 3 plus 3. 3 plus 3 is 6, so this is true statement. Now we have to check our Q. Q is 8 is less than square root of 69. Square root of 69 is greater than 8, so this is true statement 2. We have true implies true. So our statement is true. This is my solution. We have to classify if our statement is true or false. So first we have to determine our simple statements. First statement is 6 equals 3 plus 3. This will be our P. And 8 is greater than square root of 69. This is our Q. We have implication here. P implies Q. And we know that implication is only false when P is true and Q is false. So we have to now check our P statement. P is of course true because 6 is equal 6. And Q we have 8 is greater than square root of 69. Square root of 69 is approximately equal 8.3. So 8 is greater than 8.3? No, it's not true. So Q is false. So we have that from true we have false. True cannot imply false. So this is false statement. This is my solution. We have biconditional statement here because we have this symbol. This symbol represents words if and only if, and we use this symbol for these words. Let me write this for this symbol. This symbol represents words if and only if. So we have biconditional statement. Now we have to determine our first simple statement. Is 6 is different than 3 plus 3. This will be our P. And 8 is less than square root of 69 will be our Q. So P if and only if Q we have. Next we have to check our P and Q statements if they are true or false. We know that biconditional statement is true only when both statements are true or both statements are false. So we have P is 6 is different than 6? No, it's not true. So this is false. And we have Q. 8 is less than square root of 69? Of course. So this Q is true. We have false if and only if true is not true statement. One more time, the conditional statement is true only when both statements are true or both statements are false. So this statement is false. One more time, let me rewrite this. We have P if and only if Q is false. This is my solution. We have given statement, the conditional statement. Why? Because we have this symbol. This symbol represents if and only if. And when we have these words between two statements, this is the conditional statement. So now we have to first determine simple statements. So 6 equals 3 plus 3 is our simple statement. So this is our P we can write. And 8 is less than square root of 69. This is our Q. And we have P if and only if Q. The conditional statement is true only when both statements are true or both statements are false. Let's check. Our P is 6 equals 6. Yes, this is true. And Q is 8 is less than square root of 69, of course. So this is true. So we have true if and only if true. This is true statement. So we have P if and only if Q is true statement. One more time. Why? Because B conditional statement is true only when both statements are true, like in this example, or both statements are false. This is my solution. We have given statement and we have to classify if it's true or false. First, we have to determine simple statements. So first simple statement will be 4 plus 3 equals 8. This is our, let me put P. And next we have 8 plus 10 is different than 18. This will be our Q. We have word or between these two statements, between these two simple statements. So or represents our symbol, this, and this is for disjunction. So we have P or Q. Disjunction is false only when both statements are false. So let's check first statement. P is simple statement. 4 plus 3 equals 8. 7 equals 8. No. So this is false. Q is 8 plus 10 is 18. 18 is different than 18. No. So this is false. So we have false or false. When we have disjunction false or false, this is false statement. Like I said before, disjunction is false only when both statements are false. When one of them is true or both true, our statement will be true. But both are false, so our statement P or Q is false. This is my solution. We have to classify if our statement is true or false. So let's read the statement. We have the area of square A side is 2a, or it is a square. So we have here word or. It means we have the disjunction statement. For disjunction statement we use symbol like this. And first we will find simple statements. First simple statement will be the area of square is 2a. So let's put that our P is the area of square is 2a, A is side, and Q will be our second simple statement, and will be the area of square is a square. So now we have to decide if P and Q statements are true or false. So P is the area of square is 2a. No, it's not true statement. So this is false. And Q is the area of square is a square. A is side of square, of course. So this is true. So we have here disjunction P or Q. P is false. We have P or Q is true. And we know that disjunction is false only when both statements are false. In this example, one of statement is true. So our disjunction will be true. This is my solution. We have here statement if x and y are integer with x minus y is greater than 0 and y minus x is greater than 0, then x equals y. First, we have word here if and then. If means we have implication here. For implication, when we have if, then we use symbol like this, or sometimes we have doubles line with arrow at the end. And next we have comma. It means we have to keep statement of the left side together and on the right side together. Next we have here word and it means that we have here conjunction on the left side. If x and y are integer with we have x minus y greater than 0 and y minus x greater than 0, then x equals y. Let's first find simple statements. First simple statement will be, and let's put that this will be our, because we have word and, so we have this, for example, r. Next, y minus x will be our s. So we have if r and, for and word we use symbol and. This means we have conjunction on the left side, r and s. We have to put this in parentheses because we have comma, so we have to keep together these two sentences. And then x equals y. This is our, for example, P. So now we have implication here. We know that implication is false only when hypothesis is true and conclusion is false. So on the left side we have r and s. R is x minus y. And we know that x and y are integers. So this is like -2, -1, 0, 1, 2, and so on. We're going from negative infinity to positive infinity. So let's choose two numbers. For example, for x, we can put -10, and y will be our -5. So now we have r is x minus y. So we have, let me copy this, x. Our r is, and we will have x minus y. So this is equal, x is -10 minus, we have -5. So this is equal -10 plus 5 is equal -5. So this is less than 0. And when we take s is y minus x, so this is equal -5 minus -10. This is equal -5 plus 10 is equal 5. So this is greater than 0. So we see that for x equals -10 and y equals -5, we have r is -5. So this is less than 0. X minus y is greater than 0. We got that x minus y is less than 0. So this is false. And y minus x is greater than 0. So this is true. We have between r and s conjunction. And we know that conjunction is true only when both statements are true. We have that r is false and s is true. So our conjunction is false. So we got on the left side false statement. When we have on the left side false statement and we have here implication, let me rewrite this, r and s imply p. On the left side we have false. So now it doesn't matter what value has our conclusion, because our hypothesis is false. It doesn't matter what we will get on the right side. Implication is only false when we have true hypothesis and false conclusion, because we got on the left side that this statement is false. It doesn't matter what we have on the right side, true or false. When we have implication, false imply true or false imply true is always true statement. So our statement, if x and y are integer with x minus y greater than 0 and y minus x greater than 0, then x equals y is true statement. And what else we can say? We know that conjunction is true only when both statements are true. So x minus y must be greater than 0 and y minus x is greater than 0 when x and y are integer. This is impossible, but both statements will be true. So that's why our statement will never get true on the left side. We always get false. That's why our statement is true. We have given set A, and this set has elements 1, 2, 3 to 15 numbers, and we have to determine the true value of a statement. This symbol means there exists. Let me rewrite this. This symbol means so let's read this statement. There exists x, and x belongs to set A such that x plus 4 is equal to 20. So let's check our A set. A has numbers 1, 2, 3, 4, 5 until 15. So can we find number x from this set, and when we add to this number 4 we will get 20? The largest number in this set is 15. 15 plus 4 is 19. It's not 20. So this statement is false. Why? Because for no number in A set is a solution. Because we cannot find any number from set A for which x plus 4 will be equal 20. So this is false statement. We have given set A, and this set has elements 1, 2, 3, 4, 5, 6 until 15. And we have to determine the true value of statement. This symbol means there exists. Let me write this. This symbol means there exists. So we have there exists x belongs to A such that x plus 4 is less than 6. Because we have here there exists, it means will be enough if we find one number from this set such that for this number, when we add 4, it will be less than 6. If we choose that x 0 is equal 1, we will have 1 plus 4 is equal 5, is less than 6. So this inequality will be true. 5 is less than 6. It means there exists one number, for example, x equals 1, and it will be enough because we have varies exist. It's enough if we find one number from this set. For x equals 1, this inequality is true. So this statement is true. This is my solution. We have given set A, and this set has elements from 1 to 15. We have to determine the true value of statement. This symbol means for all x. Let me write this. This means for all x. So we have for all x belongs to set A, x plus 4 is less than 20. We have here the smallest number is 1. So let's put that x 1 is equal 1. We will have 1 plus 4 is equal 5, is less than 20. And the largest number from this set is 15. So let's choose x2 is equal 15. We will have 15 plus 4 is equal 19. 19 is less than 20. So for the largest number from this set, this inequality is true. It means that this inequality will be true for all x's from this set. So this statement is true. We have given set A and has an element from 1 to 15. The smallest number is 1, the largest is 15, and we have to determine the true value of a statement. This symbol means for all x's. So let's write this. This means for all x's. So from all x's from this set, this inequality must be true because we have this symbol for all x's. So let's check. When we will take x1 equal 1, we will have 1 plus 4 is equal 5 is less than 9. And now when we choose the largest number, for example, x2 is equal 15, we will have 15 plus 4 is equal 19. If 19 is less or equal 9, no, it's not true. Because this quantificator means that this statement must be true for all x's, and we found example for x equals 15. This inequality is not true. It means that our statement is not true, so it's false. When we have this quantificator, it means that this statement must be true for all x's from this set. It's not true because we found that for x equals 15, this inequality isn't true. It means our statement is false. This is my solution. We have given set B, and B set has elements 1, 2, 3, 4. And we have statement. This symbol means for all x. Let me write this. And next we have for all y. And x and y belong to set B. X squared plus y squared is less than 24. When we have this symbol, which means for all x, it means whatever you choose. 1, x equals 1, x equals 2, x equals 3, x equals 4. This inequality must be true. If I choose that x is equal, for example, 3, and y is equal 4, we will have x to second power. So we have 3 squared plus y is 4. 4 to second power is equal 3 to second power is 9 plus 4 to second power is 16. So this is equal 25. 25 is not less than 24. It's not true inequality. So it means because we found example for which this inequality is not true, it means that this statement is false. This is my solution. We have given set B, and B has elements 1, 2, 3, 4, and we have statement. This symbol means for all x. Let me write this. And this symbol means there is y. There exists y. So we have for all x from set B, there is exist y from set B such that x plus y is less than 10. So let's check. We have only 4 elements. So first, because we have for all x. So we have to choose x equals 1, x equals 2, 3, 4. Because they are small numbers, so we can always choose y from this set that this inequality will be true. Let's do this. For x equals 1, there exists. So we can choose y equals 1. We will have 1, let me copy this, x plus y is equal 1 plus 1, this is equal 2, is less than 10. So this inequality is true for x equals 1. Next we have in this set x, let's put this is x1, x2. We can choose, for example, y equals whatever from this set. So can be 4, for example. This is y1, y2. So we will have x plus y is equal 2 plus 4. So this is equal 6. 6 is less than 10. So this inequality is true for x equals 2. The same we can do for x equals 3 and x equals 4. Because these numbers are very small and we can always choose for y smaller number, or if we choose 4 it still will be true because 4 plus 4 will be 8 is less than 10. It means that for all x from this set we always can find y belongs to the same set, that this inequality is true. So because it's true for all x, so this statement is true. We have given set B, which has elements 1, 2, 3, 4, and we have statement. This symbol means there exists, so let me write this, there exists x and this symbol is for all y. So let me read this now. Where exists x belongs to B for all y belongs to B such that x cubed is less than y plus 1. So let's see. If x equals 0 equals 1, then every y we can choose 1, 2, 3, 4. We choose y from B set. Are all solutions to, and we will have 1 to third power will be still 1 is less than, and when we put 1 will be 1 plus 1 is 2, is 1 is less than 2. When we put for y0 2, we will have 2 plus 1 is 3, is greater than 1. When we put 3 for y0, we will have 3 plus 1 is 4, is greater than 1. And when we put y0 equals 4, so we have 4 plus 1 is 5, is greater than 1. So for all y, this inequality is true. So this statement is true. We have given B set, and this set has elements 1, 2, 3, 4. We have given statement. This symbol means for all x. So we have for all x belongs to B set. Absolute value of x is equal x. Because we have here only positive numbers, So this statement will be always true, because absolute value of 1 is 1 and 1 belongs to this set. Absolute value of 2 is 2, 2 belongs to this set. Absolute value of 3 is 3 and 3 belongs to this set. And absolute value of 4 is 4. So this statement is true for all x from this set. So our statement is true. We have to negate the following statement. X is an integer and x squared plus 2 is equal 0. So let's put that P is simple statement. X is an integer. This is our P. And the second simple statement, x squared plus 2 equals 0, is our Q. Because we have word and, it means we have conjunction P and Q. And negation of conjunction. For negation, I use symbol this. Sometimes in book we have something like this. So negation of conjunction we have here. So this is equivalent to, we use De Morgan's law, not P or not Q. I just use De Morgan's law. So we have negation of conjunction. We have not P. So P is, x is an integer. So we will write x is not an integer. Next we have or. This symbol means or. And we have negation of Q. X squared plus 2 equals 0. This is our Q. So negation, so will be x squared plus 2 is different than 0. This is our solution. We have statement, every integer is divisible by prime. When we have word every, for negation of, we used there exists. So we will have there exist, and the rest we have to integer, copy. And now we have every integer is divisible by prime. So when we have negate this statement, we will have there exists integer that is not divisible by prime. This is my solution. We have statement, if she swims, then the water will be warm. Because we have here if and then, it means we have implication here. Let's put that she swims will be our P and the water will be warm, our Q. So we have implication P imply Q. And we have to find negation of implication. So negation of implication is equivalent to conjunction P and not Q. So we have P is our she swims. And the water, we have negation of Q, so will be the water will not be warm. This is my solution. We have statement, all students completed their homework and the teacher is present. Let me put that our P will be first part, all the students completed their homework, and Q will be the teacher is present, our Q. Because we have word and, it means we have conjunction statement here, P and Q, and we have to find negation of conjunction. This is equivalent from De Morgan's law to not P or not Q. So I just use De Morgan law. So we have not P. Negation of for O is negation, let me write this, for O is some. So we will have some student of the students completed, so negation will be did not complete their homework. And now we have to put symbol for disjunction. So we have or, and negation we have to write for the second statement. The teacher is not present. So we can write absent. In other words, so this is my solution. It means for not present, we can always write absent. The teacher is absent. This is my solution. We have to find negation of statement he is rich or he is happy. So first, let me put that he is rich is our P and Q will be his happy. So because we have word or, it means we have disjunction statement P or Q. And we have to find negation of P or Q. From De Morgan's law, this is equivalent to not P and not Q. So we have to negate first sentence, simple statement, and the second simple statement. So we have he is rich, so will be he is not rich. And because now we have conjunction and we have he is happy, so negation will be he is not happy. We can rewrite this sentence and we can write he is not rich, so he is poor. And he is not happy, so he is unhappy. This is my solution. You can use the first sentence and the second, both are correct. We have statement there exist x, y, and z such that x times in parentheses y times z is different than x times y times z. Negation of there exist is for O always. When we have there exist, we use word for negation for O. So we have for O, x, y, and z, we have different, so negation will be equals x, and in parentheses y times z equals x times y times z. So this is my solution. We have given statement where exists x for all y such that p of x of y. We have to find negation of there exists x for all y that p of x of y. This is equivalent to, and negation of there exists is for all, so we have to use quantificator for all. Negation of for all is there exist, y of course, that not p of x of y. We have to negate this expression. So this is my solution. We have given statement for all y belongs to R. R is all real numbers. Y plus 5 is greater than 8. We have to find negation of for all y belongs to all real numbers. We have that y plus 5 is greater than 8. This is equivalent to, when we have negation, it means we have to change quantificator. When we have for all, it means there exists, negation is there exists y, and y belongs to real numbers such that y plus 5, and we have to negate this inequality. So we have y plus 5 is greater than 8 when we have negation, so will be y plus 5 is less than or equals 8. This is my solution. We have given implication. Let's put that x squared plus 4 is our p and x equals 2 or negative 2 is our q. We have implication p imply q. First we have to write converse. When we have implication p imply q, the converse for this implication is, let me write this, is q imply p. So we will have, first we have to put q, so this is x is equal to or negative 2 imply x squared equals 4, because x squared plus 4 equals 4 is our p. It's our formula. Now we have to write contrapositive of the following implication. We have p imply q, contrapositive, is not q imply not p. So we will have to negate our q statement and have to negate our p statement. So we have, let me write this. This was our converse. And now we have to find contrapositive. So we have not q. Q is x equals 2 or negative 2 imply not p. P is x squared equals 4. We can rewrite x equals 2 or negative 2. So we have negation of x equals 2 or x equals negative 2. This is equal exactly what we have here. X equals plus or minus 2. So x equals 2 or x equals negative 2 we have. And this implies that x, and we have negation of x squared equals 4. It's negation of equation we have. So we have x squared is different than 4. And here we have this junction we have x equals 2 or x equals negative 2. This is negation of disjunction, and for negation of disjunction we use De Morgan's law. When we have, for example, negation of R or S, this is equivalent from De Morgan's law that not R and not S. So we will have not x equals 2 and not x equals negative 2. And this implies x squared is different than 4. When we have negation of equation x equals 2, so we will have x is different than 2 and x is different than negative 2. We can put this whole expression in parentheses because this conjunction implies that x squared is different than 4. This is our contrapositive of our implication. P imply Q. This is my solution. We have given implication. If 5 plus 5 equals 10, then 6 plus 6 equals 12. Let me put that 5 plus 5 equals 10 is our simple statement P, and 6 plus 6 equals 12 is our simple statement Q. So we have implication P imply Q. We have to find converse. The converse of implication P imply Q is, let me write this, converse is Q plus P. So we have Q is our 6 plus 6 equals 12. So we have if 6 plus 6 equals 12, then, and now we have to put here, 5 plus 5 equals 10. We have to find contrapositive. Contrapositive of implication is not Q implies not P. So we have to negate Q and P statement. So we have if, and we have not Q, so negation of for equation we have here, so it will be 6 plus 6 is different than 12, then negation of equation again, so we have 5 plus 5 is different than 10. This is my solution. We have implication if x times y equals 0, then x equals 0 or y equals 0. We have to find converse and contrapositive. So first let me put that our P is x, y equals 0 and our Q is x equals 0 or y equals 0. We have implication P implies Q. Converse is, for this implication, is Q implies P. So we will have that if x equals 0 or y equals 0, then x, y equals 0. I can put this in parentheses, first part. So this is our converse, and now we have to find contrapositive. Of our implication, P implies Q is not Q implies not P. So we will put this in parentheses, not Q, so we have x equals 0, or this is disjunction statement, So I can use symbol like this. So we have or y equals 0. Then we have negation of p. So x, y equals 0. We have here negation of disjunction. So we will use De Morgan's law, negation of disjunction. So let me put when we have statement R or S. This is equivalent from De Morgan's law, not R and not S. So we have on the right side conjunction not R and not S. So we will have our R is x equals 0 and our S is y equals 0. So this is equivalent from De Morgan's law to not x equals 0, and we have now symbol of and, not y equals 0, and we have then and negation of equation we have here. So negation will be x, y is different than 0. So now again we have negation of equation, so x is different than 0 and y is different than 0, then x, y is different than 0. This is my solution. We have implication. If x is greater than 0, then x squared is greater than 0. Let me put that x is greater than 0 is our p, and x squared is greater than 0 is our q. We have to find converse of this implication. We have implication p implies q, so we have converse is q implies p. So our q is x squared is greater than 0. So we have x squared. If x squared is greater than 0, then p we have x is greater than 0. This is our converse and contrapositive. Now we have to find contrapositive to implication p implies q is not q implies not p. So we have negation of q. So we have not x squared is greater than 0. If not square x squared is greater than 0, then negation of p we have not x is greater than 0. So we have negation of inequality. X squared is greater than 0, so we have x squared is less than or equals 0. If x squared is less than or equals 0, then x is less than or equals 0. We have to write negation of inequality x is greater than 0. We can rewrite this. If x squared is less than or equals 0, then x is less than or equals 0. This is my solution. We have given implication. If the earth is flat, then Julius Caesar was the first president of United States. So first let me put that our P simple statement will be the earth is flat. And Q will be Julius Caesar was the first president of United States. This is our Q. We have implication P implies Q. We have to find now converse of this implication. The converse is Q implies P. So we have to rewrite our sentence, and we will have first to put Julius Caesar was the first president of the United States, and of course I forgot, we have to put if Julius Caesar was the first president of United States, then we have statement the earth is flat. This is our converse to implication, to give an implication. Now we have to write contrapositive of implication P implies Q is not Q implies not P. So we have first to put negation of Q. Because we have implications, so we have to use at the beginning word if, and we have to negate this first statement. So it will be if Julius Caesar, negation, we have was the first, so it will be was not the first president of the United States, then, and now negation of P statement, the earth is flat, so will be the earth is not flat. Then the earth is not flat. So this is my solution. We have given implication. If triangle ABC is right triangle, then A square equals B square plus C square. So let me put that our simple statement is ABC is right triangle. This is our P. And A square equals B square plus C square is our Q. We have implication P imply Q. First we have to write the converse of if P then Q. We have if Q then P. So we have first our Q statement, simple statement. So we have if A square equals B square plus C square, then we have triangle ABC is right triangle. Now we have to write contrapositive. So we will have contrapositive for if P then Q is if not Q then not P. So we have to negate Q first. So we have if negation of equation is will be A square is different than B square plus C square, then and negation of triangle ABC is right triangle will be triangle ABC is not right triangle. This is my solution. We have to determine the true value of compound statement, and we have given that P, the simple statement, is false. Let me write this here. P is false. Next, we have given that Q is true and R is true. In this example, we have only R. So R, the simple statement, is true. And we have here conjunction statement. Conjunction statement is true only if all of components of a statement are true. So let's see what we have here. We have parentheses. So first we will check what we have in parentheses. P or R. So we have here disjunction. Disjunction is false only when both simple statements are false. We have that R is true. So it means that P or R, you can put this in parentheses, is true. Why? Because R is true. P is false, but is enough when one of these components is true to be disjunction true. So we have in parentheses true. Before parentheses we have negation. So we have negation of disjunction P or R. We have in parentheses true. So when we have negation of true, so this is false. And on the right side we have R. R is true. But because we have here conjunction, and for conjunction statement to be true, it is necessary that all of components of statement be true. Because the first part, this, is false, it means that this compound statement is false. So let me write this, that not P or R and R is false. Why? One more time. Because we have this part false. And conjunction is true when both components are true. So this is my solution. We have given compound statement and we have that P is false. Next we have that Q is true. And R, the simple statement, is true. So let's see what we have here. We have disjunction statement because we have this symbol OR. So we know that disjunction is true is enough if one of this component is true. So let's see what we have here. Inside this bracket we have parentheses, so we will start inside. We have P and negation of Q. So we have negation of true. Negation of true is false. So we have not Q is false because Q was true. Next we have P and not Q. So let me write this. P and not Q. P is false. And we know that conjunction is true when both of components are true. So because P is false and negation of Q, we have not Q is false. So it means this is false. Next, we have OR. So we have here disjunction. Disjunction is false only when both simple statements are false. R is true. So it means that this whole expression in brackets is true. So let me copy this. P and not Q or R is true. Why? Because R is true and we have disjunction here, and disjunction is true when one of these components is true. So we have that this brackets, whatever we have in this brackets, is true. Because we have or between these two statements, so we know that this whole compound statement will be true. Why? One more time. Because we have here disjunction. Disjunction is true when one of these components is true. Because whatever we have in brackets is true, it means that this whole compound statement is true. Let me write this. We have P and not Q or R in brackets, and we have or, and in parentheses we have P and not Q. So this is true. This is my solution. We have here between these brackets and braces symbols or, and inside these braces we have or. It means we have here disjunction statement. Disjunction is false only when all of these simple statements are false. So let's see first what we have in brackets. We have P and in parentheses we have Q and R. So we have here conjunction. We know that conjunction statement is true when all of these simple statements are true. We have that P is false. It means this whole statement in these brackets is false. So let me write this. P and in parentheses we have Q and R is false. Next, let's see what we have in braces. We have here brackets, and between these two brackets we have symbol or. It means we have again disjunction. So let's check first what we have in this first brackets. We have not P, because P in parentheses we have not P and not Q. We know that again we have here conjunction statement to be true. It is necessary that all of components of a statement are true. So because we have here negation of P, so we have, because P is false, so negation of P will be true. And we have negation of Q, because Q is true, so not Q is of course false. So in this parenthesis we have false statement. So we have not P and not Q is false. Why? Because we have conjunction and one of this component is false. Not Q is false. It means this whole statement is false. So because this is false, so next we have again conjunction. Because expression in parentheses is false, it means this whole statement, because this is conjunction, is false. So we have in brackets not P and not Q, no and R is false. So first expression in brackets is false. The second expression in brackets is false, so we have to check the last. So let's see what we have here. We have P and Q. Because P is false and we know that conjunction to be true, it is necessary that both of simple statements are true. Because P is false, it means that P and Q is false. Next, we have again symbol AND. It means we have in this bracket conjunction. For conjunction statement to be true, it is necessary that all of components of the statement be true. So because P and Q is false, it means this whole expression in brackets is false. So let me write this. P and Q and not R is false. We got that expression in first bracket is false. Expression in braces, first is in brackets false, and the second is false too. So because we have between these statements symbol OR, and we know that this junction is true and one of the statement must be true. Because we got that all of the statements are false, it means that this compound statement is false. So we can rewrite this whole compound statement. We have P and in parentheses Q and R, close brackets, or and in braces we have brackets, not P in parentheses and not Q and R, or in brackets not P and Q and not R, close braces. So this is false. One more time, because we have here disjunction, and disjunction is false when all of components are false. This is my solution. We have given that P is true statement. Let me write this. P is true. And we have compound statement P or not Q. What we can say about this compound statement? Because we have here symbol OR, it means we have disjunction, and disjunction is false only when both simple statements are false. Because P is true, it means that this compound statement is true. This is my solution. We have given that R is false statement. So let me write this. R is false. And what we can say about this compound statement? We have in parentheses P or Q, and we have and R. Because we have here symbol and, it means we have conjunction, and we know that conjunction statement to be true is it necessary that all of components of the statement be true. Because R is false, it means that this whole compound statement is false. It doesn't matter what we have in parentheses. So this is false. Why? Because R, the simple statement, is false, and we have here conjunction, and conjunction to be true, it is necessary that all of the components of the statement are true. This is my solution. We have to construct a truth table for compound statement. Because we have here two simple statements P and Q. So we start with a standard form that has 2 to second is equal 4 rows. So we have to put in first column, we will put P. Next we have Q. Because we have here not Q, so the third column will be not Q. And next we have to put our compound statement because we have P and not Q. So we have P and not Q. Now first we have to put our combination for P and Q. P can be true or false, and Q statement, simple statement, can be true or false. In some book you can have for true symbol T or 1, and for false you can have capital letter F or 0. You can use T, F or 1, 0. I will use 1 and 0. So when P is 1, it means true, Q can be 1. When P is 1, Q can be false, so it's 0. And now when P is false, Q can be false. And when P is false, Q can be true, so this is 1. So now we have not Q. When we have 1, so negation of 1 is 0. Negation of 0 is 1, negation of 0 is 1, and negation of 1 is 0. Next, in the last column, we have P and not Q. When we have symbol and, it means we have here conjunction. So we know that conjunction is true only when both statements are true. Simple statements. P, in first row we have P is true and not Q is 0. So 1 and 0 give us 0. Because conjunction is true only when both statements are true. Next we have 1 and 1, so this is 1. 0 and 1, so this is 0. And 0 and 0, so this is 0. One more time, conjunction statement we have here, and conjunction is true when both simple statements are true. So that's why we got something like this. This is my solution. We have to construct a truth table for compound statement. The given statement, which we have here, in parentheses we have not P or Q, or, and in brackets we have negation of, and in parentheses we have R and not Q. We have here simple statements P, Q and R. It means that the standard form has 2 to third is 8 rows. So next, in first columns, we have to put first our simple statement. So we have P, next we have Q, R. Next we have to check if we have negation of simple statement. We have not P, so next would be not P. What else we have? We have not Q. Next, we have to put statements which are in parentheses. We have in parentheses first not P or Q. And in brackets, we have parentheses R. First, I will put whatever is in parentheses R and not Q. And next we have to put negation of this parenthesis. So we have not and in parenthesis R and not Q. Next, so we have this brackets in last column, and next we have to now put this whole compound statement. So we have not P or Q, or, and in brackets we have not, in parentheses we have R and not Q, close brackets. So now we have to first write our combination of simple statement. P can be true. In some books we can find for true they put T. And in some books you can find that for true is 1. And for false is F, or in some book you can find 0. I will use 1 and 0. So when P simple statement is true, we can put 1. For Q, 1, and R is true first, so is 1. Next, we can have that. First is 1, 1, 0. Third row will be 1, 0, 0. So next we can have that first simple statement is true, Q is false, R is true. Next we will have P is false, Q is true, R is false. What else we have? 0, 0, 0. All of simple statements are false. And we can have 0, 0, 1, 0, 1, 1. So this is our combination for simple statement P, Q, R. Next we have negation of P, not Q. So when we have that P is 1, so not P is 0. It means false. Not P, so again we have 1, so it will be 0. 1, so it will be 0. 1, so it will be 0. For 0, negation of 0, negation of false, not false, is 1, true. For 0 is 1, 1, 1. Next we have not Q, so we have to use the second column, and for 1, not 1, not true, so this is false. 0, 0, 1, 1, 0, 1, 1, 0. And next we have here disjunction, because we have symbol OR. Disjunction is true when one of a simple statement is true. Enough is false when both simple statements are false. So let's look now in, we have negation of P or Q. So we use second and fourth column. We have 1, 0, so it will be 1, 1, 0, so it will be 1, 0 and 0, so it will be 0, 0 or 0, so it will be 0, 1 or 1, so it's 1, 0 or 1, so this is 1, 0 or 1, so 1, 1 and 1 or 1, so this is 1. Next we have here in parentheses conjunction. Conjunction is true when both simple statements are true. So we have to check R and negation of Q we have. So we have 1 and 0, so this is 0. 0 and 0, so it will be 0. 0 and 1, so this is 0. 1 and 1. Conjunction we have, so this is 1, 0 and 0 will be 0, 0 and 1, 0, 1 and 1, so it will be 1, and 1 and 0, so will be 0. Next, we have negation of statement which we have before. So we have to look only for this. For 0, negation of 0 is 1, not 0, so will be 1, 1, 0, 1, 1, 0, 1. And in last column, we have disjunction between these two statements. And these statements we have in this column and this. So we have to compare only these two columns, and we have symbol OR, so it means we have disjunction statement, and we know that disjunction statement is false only when both statements are false. So we have 1 or 1, so it will be 1, 1 or 1, so 1, 0 or 1, so it's 1, 0 or 0, so now we have false. 1 and 1 is 1, 1 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. The last column is our truth table for our compound statement. So this is our solution. We have to construct a truth table for a compound statement. We have here simple statements P, Q, and R. So the standard form that has 2 to 3rd, because we have simple statement P, Q, R is 3 simple statements, so we have 2 to 3rd, so this is 8. So we have to have 8 rows in our standard table. And next we have to just put in the first 3 columns combination of P, Q, R. P can be true or false, and Q the same, R the same. So for false, we can use symbol F or 0, and for true, we can use T or 1. It means the same. For false, we use 0, and for true, 1. I will use 0, 1 because it's easier for me. I like this. So we have P, column, Q, next, R. In the next column, we have to check if we have negation of simple statement. We have negation of P, so we put not P. Next, we have negation of Q, so will be not Q. Next, we have to check first in parentheses. If we have parentheses, we have statement in parentheses, not P or R. So let's put this not P or R. Next, we have negation of not P or R. So we will put not P or R. In next column, we have to, so it was expression in brackets. Now we have to put this whole statement which we have in braces. So it will be not and first brackets, not P or R, and we have and Q. In the next column, we have in parentheses R and not Q. And in the last column, we will have to put this whole compound statement. Because I don't have enough place, so I will put that this is our first part, this is our second part, and between 1 and 2 we have and 2, so we have here conjunction. So now we have to put first our combination for simple statement PQR. P can be true, Q can be true and R can be true. Now let's put that P is 1, Q is false, so 0, R is 0. Next we can put 1, 1, 0 we can put. Next we can put 1, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 1. And now we will have P is false, Q is false, and R is false. So we have all combination. You can always check. When we have 8 rows, you should have P true 4 times and 4 times false. The same for Q. 1, 2, 3, 4 zeros and 1, 2, 3, 4 ones. And for R we have to have 4 trues and 4 false. So everything is okay. Next we have negation of P. So not true, so this is 0, false, not true, 0, not true, so 0, 0, not false, so this is true, 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 true. Next we have negation of Q, not Q. We have first 1, so this is true, not true, so will be 0, not 0, so this is 1, 0, 1, 0, 1, 0, 1. Next we have here disjunction. We know that disjunction is false only when both simple statements are false. So we have to look now for not P and R. So with 2 columns, and we have or. So 1 or 0. So this is 1. 0 or 0. So this is 0. 0 or 0 is 0. 1 or 0. This is 1. 0 or 1. This is 1. 1 or 1. 1. 1 or 1. 1. 0 or 1. So it's 1. Next we have negation of this whole statement. We have not P or Q. First we have not 1, so this is true, not true, so this is 0, not false, so this is 1, 1, 0, 0, 0, 0, 0. Next we have conjunction between these 2 statements. We have not and in parentheses not P or R, and we have and Q. So we have to look for this column and second column. So we have and. So conjunction is true when both of statements are true. We have 1 and 0, so this is 0, 0 and 1, so this is 0, 1 and 1, so 1, 0 and 0, 0, 1 and 0, 0, 0 and 0, 0, 1 and 0, 0, 0 and 0, so this is 0. Next we have R and not Q. R, so this is third and fifth column. We have conjunction. We know that conjunction is true when both of statements are true. When we have 1 and 0, so this will be 0, 0 and 1, 0, 0 and 0, 0, 1 and 1, so this is true, 0 and 0, false, 1 and 1, so this is true, 1 and 0, so this is 4, 0 and 1, so this is 0. And in the last column we have truth table for this whole component. So we have to look in this column, because in this column we have our expression in braces, and we have no and the last our column. Because we have symbol and, it means we have conjunction. So conjunction is true when both of statements are true. We have 0 and 0, so this is 0, 0 and 0, 0, 1 and 0, so this is 0, 0 and 1, so 0, 0 and 0, 0, 0 and 1, 0, 0 and 0, 0, and 0 and 0, so this is 0. So the last column is our truth table for compound statement. This is my solution. We have given two statements and we have to show that they are equivalent statements. So first we will construct two truth tables and we will compare the results. We have P and Q simple statements. P and Q. So it means we will have 2 to second power, so this is 4 rows. In first column we will put P, next this is Q, simple statement, and we have P or Q. So we will put P or Q in the third column because we have 4 rows, so we will have P can be true. For true, you can use symbol T or 1. For false, we can use F or 0. I like to use 1 and 0. So we can have that P simple statement is true and Q statement is true. We can have that P is true, Q is false, P is false, Q is true, and P is Q, and Q is P is false, and Q is false. Next, we have P or Q statement. We have disjunction. Disjunction is false only when both simple statements are false. So in the first row we have 1 and 1, true and true. So 1 or 1 is true, 1 or 0 is 1, 0 or 1 is 1, and we have false and false, so this is false. The third column is our truth table for first. This is our truth table for P and Q for first statement. Next we will build truth table for the second statement. We have again P and Q. So we have in first column P, in the second Q. Next we have negation of P, so we have to put not P. Next we have to start from parentheses. In parentheses we have Q and not P, and next we have P or Q and not P. So the last column is P or Q and not P. So now in the first two columns we have to write all combination. P can be true or false and Q can be true or false. So it can be 1 and 1. We have to use exactly the same like we have in the first table. When P is, because it will be easy to compare the result. P is 1, Q is 1, so it's the same. Next 1, 0, 0, 1 and 0 and 0. Next we have negation of P. So if P was 1, so now will be 0, 0, 0, so now will be 1, 1. In the fourth column we have conjunction Q and not P. We know that conjunction is true when both of statements, simple statements, are true. So we have negation of P and Q. 1 and 0, so this is 0, 0 and 0, 0, 1 and 1, so this is true statement. 0 and 1 is 0. In the last we have symbol OR, so we have disjunction, and disjunction is false only when both statements are false. So we have to look for P and the fourth column. We have 1 or 0, so this is 1, 1 or 0, this is 1, 0 or 1, so this is 1, and 0 or 0, so this is 0. Now we have to compare the results. The true table for P on Q, or Q is in this column, and true table for P, or in parentheses we have Q and not P is in the last column. We see that we have identical true values. 1, 1, 1, 1, 1, 1, and 0 and 0. Always you have to have the same values for P and Q, for first statement and for the second statement. Don't mix, because if you mix, it will be difficult to check. When we have the same values for P and Q, it's very easy to compare only the last columns. Because we have identical true values, it means that our statements are equivalent. This is my solution. We have given two statements and we have to check if they are equivalent statements. So because we have simple statements PQR are simple statements, and because we have three simple statements, it means we will have 2 to 3rd, so this is 8 rows. So first we have to put our combination for P, Q, and R. It will be 8 combination. P can be true, false, Q can be true, false, and R can be true, false. We have P, Q, R. Next, we have to check if we have negation. First, we build truth table for the first statement. We have negation of Q, so we have to put not Q. Next column, we have negation of R. Next, we have to check first what we have in parentheses. We have not Q or not R. And we have not P and all these parentheses. So we have not P and not Q or not R. So this is our last column. Next, we have to write this 8 combination. P can be true, Q true, R true, 1, 1, R can be 0, it means false. In some books, you can find that for true, they use T or 1. For false, you can use F or 0. I like to use 1 and 0. So we have 1, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0 can be 0, 0, 1, 0, 1, 1. You can always check. You should have in first column 4 ones and 4 0, in the second the same 4 ones and 4 zeros and 4 ones and 4 zeros, so everything is okay. In fourth column we have negation of Q, so we'll have to look in the Q column, and negation of 1 is 0, 0, negation of 0 is 1, not 0 is 1, 0, 1, 1 of 0. Next we have negation of R, so we have to check the third column. We will have 0, 1, 1, 0, 1, 1, 0, 0. Not true is false, not false is true. So next we have disjunction, because we have OR symbol, and we have to look in the fourth and fifth column. Disjunction is false when both simple statements are false. We have 0 or 0, so it will be 0, 0 or 1. So it's 1, 1 or 1, 1, 1 or 0 is 1, 0 or 1 is 1, 1 or 1 is 1, 1 or 0 is 1, 0 or 0 is 0. Next we have to add to this column and not P. Not P. I forgot to put not P, so I will put in the front. Not P. So for not 1, so will be 0, 0, 0, 0. For not 0, so will be 1, 1, 1. And we have to look in the first column and in seventh column. So we have conjunction. So conjunction is true only when both statements are true. So we have 0 and 0, so it will be 0, 0 and 1, 0, 0 and 1, 0, 0 and 0 and 1, 0, 1 and 1, so this is 1, 1 and 1, 1, 1 and 1, 1, 1 and 0, so this is 0. Next we have to build truth table for the second statement. We have to put PQR combination in the same order which we have in the first table, because it will be easy to compare the results. So we will have P, Q, R, first we had that P is true, Q true, R Q. Next we have 1, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 1, and 0, 1, 1. Next, we have to start from parentheses. In parentheses, we have Q and R, because we don't have negation of P or Q or R, so we don't have to write this. We have only whatever is in parentheses. So we have Q and R. So we have here conjunction. Conjunction is true when both simple statements are true. So Q and R, true, true, so will be true. 1, 0, so will be 0, 0, 0, so will be 0, 0, 0, 0, 0, and 1, so will be 1. Next, we have to put P or Q and R. In brackets, we have P or Q and R. So we will have to look to the fourth column and to the first column. 1 or 1, we have disjunction. Disjunction is only false when both simple statements are false. 1 or 1 we have, so it will be 1. 1 or 0, 1. 1 or 0, 1. 1 or 0, 1. Next we have 0 or 0, so it will be 0, 0 or 0, 0, 0 or 0, 0, and 0 or 1 will be 1. Next we have negation of this whole statement, so we have to first copy this. And we will have not 1, so this is 0, 0, 0, 0, not 0, so it will be 1, 1, 1, and we have 0. Now we have to compare the results. We see that in the first truth table we have, because we put in the same order P, Q, R, so now we have to only compare the last column. Last columns we have 4, 0, 3, true and 0, and we have the same in the second truth table values. It means that our two statements are equivalent because we have identical truth values. This last column and this last column has identical truth values. It means that our two statements are equivalent. This is my solution. We have given statement, it is not true that he received a raise and he received a promotion. So first, let me put that first simple statement will be he received a raise. So let me put that P as he received a raise. The second simple statement would be Q is he received a promotion. So we have two simple statements, and we have at the beginning it is not true. So we have to negate, and in parentheses we have he received a raise and he received a promotion. So we have here conjunction P and Q. We have negation of conjunction. This is equivalent to not P or not Q. I just use De Morgan's law. De Morgan's law for negation of conjunction. This is equivalent to negation of first simple statement we have, or negation of second simple statement we have. We have not P or not Q. So now we have to rewrite our given statement. We have not P. So P is he received a raise. It means when we have to negate this simple statement, we will have he did not receive a raise. And we have next or, and we have negation on the second simple statement. We will have he did not receive a promotion. This is my solution. I just use De Morgan's law only. for negation of conjunction. We have to rewrite our given statement to equivalent form, and we have to use De Morgan's law. Let me remind you first the De Morgan's laws. When we have any statements P and Q, then when we have negation of disjunction P or Q, this is equivalent to not P and not Q. When we have negation of conjunction P and Q, then this is equivalent to not P or not Q. First, we have to find the simple statements. First simple statement is Kevin will go to the store this morning. So this is our P. P is Kevin will go to the store this morning. Next, we have he will not be able to prepare his lunch. So let's put that Q is simple statement. He will be able to prepare his lunch. And because we have here word not, so we have negation of Q. Between these two statements we have word or. For or we use symbol like this. So we have P or, and because we have not, like I said, so we have not Q. This is equivalent to, we have to use one of these laws. So because we have or, so we will use the second formula, because between these two statements we have or. This is equivalent to, we have negation of P and Q, because on the right side we have not P or not Q, and in our example we have only P on the left side, so now we have to put not P, and we have and, because we have here not Q like in this formula, so we have to now put just Q. So now we can rewrite our statement. First we have symbol not, so we will write it is not. You can write not the true that, or we can write it is not the case that. Let me put that. It is not the case that. And next, first, we have to negate simple statement P, because we have here Kevin will go to the store this morning. So when we have to put negation of P, so we will have Kevin will not go to the store this morning. And next we have symbol and we have to just copy our Q statement. He will be able to prepare his lunch. So our statement is now, it is not the case that Kevin will not go to the store this morning and he will be able to prepare his lunch. This is my solution. We have to use truth table to determine that the given statement is tautology or self-contradiction. We know that a tautology is a statement that is always true. So let's build first truth table. Because we have symbol statement P and Q, so we will have 2 to second is 4 rows. So we have to put P, Q, and we will have 4 rows, so it means 4 combination. P can be true or false, and Q can be true or false. For true, we can use T, or we can write 1. In some book you can find that for true they use T. In some you can find that they use for true 1. And for false, you can use F or 0. I like to use 1 and 0. So we have PQ. Next, we have to check if we have negation of simple statement. We have negation of P, so we will put not P. Next, we will put first parenthesis, so we have not P or Q. Because between these two parentheses we have or, so it will be easier if I now put this whole component between these two parentheses. So I will just put the symbol or in fifth columns, and in the last column I will put P or Q. Why? Because it will be easy to compare the values of these two parentheses. So in this column we have this whole statement. I just put this symbol because between these two parentheses I have or. So now P can be true, Q can be true, P can be true, and Q can be false. Now we will have P is false, Q is false, and P is false, and Q is true. You can always check. You should have 4 rows and 2 true and 2 zeros. 2 false, it means. Now in third column, we have negation of P. So we have to look in the first column. We have not 1, so this is 0. Not 1 is 0. Not 0, so this is 1, 1. Next, we have disjunction here. We know that disjunction is false only when both statements are false. So we have not P or Q. So we have to look in the second and third column. 1 or 0, so this is 1. 0 or 0, so this is 0. 0 or 1, 1. 1 or 1, this is 1. Next, we will have to do the last column. We have P or Q. So again, we have disjunction. Disjunction is false when both statements are false. Both simple statements are false. So we have P or Q. So 1 or 1, so this is 1. 1 or 0, so this is 1. 0 or 0, so this is 0. And we have now 0 or 1, so this is 1. Now, between this column, this is 1, 2, 3, 4 column, and 6 column, we have symbol OR. So we have disjunction between these two statements. In fifth row, we have this whole statement, compound statement. So we have disjunction. Disjunction, like I said before, is false only when both statements are false. We have 1 or 1, so this is 1. 0 or 1, so this is 1. 1 or 0, so this is 1. 1 or 0, this is 1. We got that our given statement is always true. Always true. It means that this statement is tautology. This is my solution. We have given statement and we have to check if it is tautology or self-contradiction. We know that statement is tautology if it is statement that is always true, and a self-contradiction is a statement that is always false. So let's first check how many simple statements we have here. We have Q and R. So we have two simple statements. It means we will have 2 to second power, so this is 4 rows. Every simple statement can be true or false. So for true, we can use symbol T or 1. And for false, we can use symbol F or 0. I like to use 1 and 0. Now we have to build truth table. First, we have to put simple statements. So we have Q, next R. Next, we have to check if we have negation of simple statement. We have not Q, so will be not Q. Next, we have to start in parentheses what we have, Q and R. So this is our second column. Next column. Next, we have negation of this statement in parentheses. So we will have not Q and R. This is our next column. Next, we have conjunction between these two statements. So we have to copy this. We have not Q and R and not Q. And next we have this whole brackets or Q. So we have Q here, so we don't have to write again. We have to just copy this whole statement. So we have not Q or R and not Q or Q. So now we have to put first all combination for Q or R. We need to get 4 rows. Q can be true, R, true, Q, true, R, false, Q, false, R, false, and Q, false, and R, true. You should have 2 truths and 2 false for Q and the same for R when you have 2 simple statements. So in third column we have negation of Q statement, simple statement. So we have not 1, so this is 0, 0, not 0, so this is 1, not false, so this is 1. Now we have conjunction. Conjunction is true only when both simple statements are true. So when we have 1 and 1. So let's see, 1 and 1, so this is 1. 1 and 0, so this is 0. 0 and 0, 0. 0 and 1, 0, of course. Now we have negation of Q and R. So when we have 1 will be 0. 0 will be 1, 1, 1. Next we have conjunction between this statement and not Q. So we have third and fifth column And we have conjunction. Like I said, conjunction is true only when both statements are true. So we have 0 and 0, so it will be 0, 0 and 1, 0, 1 and 1. So 1, 1 and 1, 1. Next, we have disjunction between this whole statement and simple statement Q. When we have disjunction is only false when both statements are false. So we have 1 or 0, so it will be 1. 1 or 0, so it will be 1. 0 or 1, 1. 0 or 1, so this is 1. We got that our statement is always true. So it means that this compound statement is tautology. Why? Because this statement is always true. This is my solution. We have given statement and we have to check if it is tautology or self-contradiction. We know that statement is tautology when it's always true and is self-contradiction when it's always false. So we need to build truth table. We have simple statement P and Q. So we will have 2 to second power rows. So this is 4 rows. P can be true or false and Q can be true or false. So for false, we can use symbol F or 0, and for true you can use symbol T or 1. It depends of books. I like to use 0 and 1. So we have to put in first 2 columns simple statements P, Q. Next we have to check if we have negation of simple statement. We have negation of P, so this is not P. Next we will check first parenthesis, so we have not P or Q. Next we have to add or, so we have not P or Q or P, and in the last column we have negation on this whole statement. So we have not and in brackets not P or Q or P. So now P, like I said, can be true or false. So we have 1. First, Q can be true or false. So let's put first true. 1 next 1, 0, 0, 0, 0, 1. We have all combination. We got 4 rows like we should, and we can always check when we have 2 simple statements, you should have 2 truths and 2 false. The same for Q. 2 truths and 2 false. Next we have negation of P. So not true, we have not 1, so this is 0, 0, not false, so this is 1, 1. Next we have disjunction. Disjunction is false only when both statements are false. Not P or Q, so we have 1 or 0, so this is 1. 0 or 0, so this is 0. 0 or 1, so this is 1. 1 or 1, so this is 1. Next we have to add to this P. We have or P. So again we have disjunction. Disjunction is false only when both statements are false. So we have to look in the 4th column and in the first. We have 1 or 1, so this is 1. 1 or 0, so this is 1. 0 or 1, so this is 1. And 0 or 1, so this is 1. Next we have negation of our 5th column. We have negation of truth, so it will be 0, 0, 0, 0. We got that our statement is always false. we have only zeros, so it means it's always false. When statement is always false, the statement is self-contradiction. So this is it is self-contradiction statement. This is my solution. We have to check if a given statement is tautology or self-contradiction. So first we have to check how many simple statements we will have here. We have P and Q, so we have two simple statements. It means we will have 2 to second power rows, so this is 4 rows. False combination, because P can be true or false and Q can be true or false. So for true, you can use T or 1. For false, you can use F or 0. I like to use 1 and 0. So in first column we will put P, next Q. Next we have to check if we have negation of simple statement. We have not P. And next step we have to check parentheses. In parentheses we have not P and Q. So this is our fourth column. And next we have conjunction between these two statements. So we have not P or Q in parentheses and P. So now P can be true, Q can be true, P true, Q false, P false, Q false, and P false, Q true. When we have two simple statements, you should have two truths and two false for P and for Q, the same. Two truths and two false. Now we have not P, so we have to check our P. Not true, so this is false, false. Not false, so this is true. Now we have conjunction. So conjunction is true only when both statements are true. So we have not P and Q, so this is true and false, so will be false, false and false. False, false and true. False and true, so will be true. Next we have again conjunction. So conjunction is true only when both statements are true. We have P and not P and Q. 1 and 0. So this is 0, 1 and 0, 0, 0 and 0, 0, 0 and 1, 0. We got that our statement is always false. So this is self-contradiction. This is my solution. We have to build truth table to determine if a given statement is tautology or self-contradiction. So first we have to check how many simple statements we have here. We have P and Q. So we will have 2 to second power is 4 rows, 4 combination, because P can be true or false and Q can be true or false. For true, we can use T or 1. And for false, you can use F or 0. I like to use 1 and 0. So now we have to put first simple statement P and Q, and we have to write all combination for P and Q. We need to get 4 rows, and next we have to check if we have negation of simple statement. We have not Q. In the next column we have to put first parentheses. So we have P implies Q. Next we have negation of conditional statement. So we have not P implies Q. And we have this symbol. This symbol is for biconditional statement. It means if and only if, and we have in parentheses P and not Q. So it will be easy when I will leave this column to this whole statement, and at the end I will put P and not Q, because it will be easier to compare these two statements, because between these two statements we have this symbol. This symbol means biconditional statement we have here. So inside, in this column, we have not P implies Q, and this is in brackets. If and only if, we have in parentheses P and not Q. So now P can be 1, Q1, P1, Q0, P0, Q0, and P0, Q1. You can always check. You should have for P 2 truths when you have two statements, P and Q, and 2 false, the same for Q. Next, we have negation of Q, so we have to look to the second column. Not 1, so will be 0, not 0, so will be 1, not 0, 1, not 1, 0. Next, we have conditional statement, and we know that conditional statement is false only when hypothesis is true and conclusion is false. So it means when we have true P and Q false. So let's see what we have here. 1 implies 1, so this is 1. 1, so hypothesis is true, conclusion is false, so this is false. 0 implies 0, so this is true. 0 implies 1, so this is 1. Next, we have negation of our conditional statement. So not 1, so will be 0, not 0 will be 1, 0, 0. Next, we have to do the last column, because we need this to this part. And we have P and not Q. So we have conjunction. Conjunction is true only when both statements are true. So we have P and not Q. 1 and 0, so this is 0, 1 and 1, so this is 1, 1, 0 and 1, so this is 0, 0 and 0, so this is 0. Now we have biconditional statement. Biconditional statement is true when we have on the left side true and on the right side true, and on the left side false and on the right side false. We have 0 if and only if 0, false and only if false, so this is true. 1 if and only if 1 we have, so this is true. Now we have false if and only false, so this is true. False and if and only if false, so this is true. We got that our statement is always true. We have only once in this column. It means that our statement is tautology. This is my solution. We have given statement and we have to build first truth table. Because simple statements are P, R, and Q, we have 3 simple statements, so we will have 2 to third power, so this is 8 rows. P can be true or false, R can be true or false, and Q can be true or false. That's why we have 8 combinations, so it will be 8 rows. And for true, we can use letter T or 1, and for false, F or 0 you can use. I like to use 1 and 0. So in first columns we have to put simple statements. We have P, Q, R. Next we have to check if we have negation. We have negation of P. And next we have to start from parentheses. We have only here parentheses. So first is not P and R, because I have only these two parentheses in the statement. So in this column I will put this whole statement, not P and R or Q or R. And in the last column I will put the last parenthesis, Q or R, because it will be easy to compare these two statements. And we have, like I said, 8 combinations. P can be true or false, the same for Q and R. So first we will have 1, 1, 1, 1, 1, 0, 1, 0, 0, 1, 0, 1. Next we can put 0, 0, 0. So all 3 statements, simple statements, are false. Next will be 0, 0, 1, 0, 1, 1, and we will have 0, 1, 0. When we have 3 simple statements, it means that we should get 8 rows. We have 8 rows, and we have to have 4 1s and 4 zeros for P, Q, E, and R. You can always check if everything is correct. Next, in the 4th column, we have negation of P. So not 1, so it will be 0, 0, 0, 0. Now not 0, so it will be 1, 1, 1, and 1. Next, we have conjunction. Conjunction is true only when both statements are true. So we have not P and R, 1 and 0. So this is 0, 0, 0, 0, 0, and we have 1 and 1, so it will be 1, 1, and 0. Next, we have to do the last column. We have Q or R, so we have this junction. This junction is false only when both statements are false. So we have Q or R, 1 or 1, so this is 1, 1 or 0, so this is 1, 0 or 0, so this is 0, 0 or 1, 1, 0 or 0, so will be 0, 0, 1, 1, 1, and 1. Now we have between these two statements symbol OR. So again we have this junction. This junction is false only when both statements are false. So we have 0 or 1, so this is 1, 0 or 1, so this is 1, 0 or 0, so will be 0, 0 or 1, so will be 1, 0 or 0, so will be 0, 1 or 1, so it's 1, 1 or 1, so this is 1, and 0 or 1, so this is 1. In this column we have our statement, which we have at the beginning. This is our statement. We see that we didn't get all 1s or all 0s. So it means that this statement is not tautology and is not self-contradiction statement. This is my solution. We have given conditional statement and we have rewrite the statement to equivalent disjunction form. Let me write: when we have P and Q simple statements, when we have now conjunction P implies Q, this is equivalent to disjunction not P or Q. In our example, we have statement if Mrs. G does not get frustrated, she will be able to complete the job. So our first simple statement will be Mrs. G does not get frustrated because we have negation here. So we have here not P. Let's write that this is not P. And the second simple statement will be she will be able to complete the job. So this is our Q. So now when we have to write equivalent form for our statement, and this form must be disjunction, we have to have, when we have P implies Q, we have not P or Q. In our example, we have not P implies Q. So this will be equivalent to, because here we have negation first of P, so we have negation of negation, we have not P, negation of not P, this is equivalent to P. So we have first P or, and next we have Q statement. So our statement will be now Mrs. G will get frustrated or she will be able to complete the job. This is my solution. We have conditional statement. If I have the money, I will buy the house. So let's put that first simple statement is I have money. This is our P, you can put. And the second simple statement is I will buy the house. This is our Q. When we have conditional statement, P implies Q, this is equivalent to disjunction form not P or Q. So we need to negate the first statement and the second we will copy. And between these two statements we have to put or because this symbol means or. So we have I and now we have to negate. So we don't have money. Or I will buy the house. This is my solution. We have given conditional statement and we have to rewrite this statement to equivalent form, disjunctive form. So let's first find simple statements. First simple statement will be frog can dance. We have if frogs can dance, then I am millionaire. So frogs can dance will be our P and I am millionaire will be our Q simple statement. So next we have conditional statement. So P implies Q. This is equivalent to disjunctive form not P or Q. So we have to negate first simple statement and the second we will copy. So we have frogs. We have to negate, so will be cannot dance. And next we have or I am millionaire. This is my solution. We have given statement and we have write negation for. We can rewrite our statement to, because we have 8 is greater than B and B is greater than C, so we can rewrite that this is equivalent to A is greater than B and B is greater than C. So let's put that A is greater than B. This is our simple statement P. And B is greater than C. This is our simple statement Q. So now we have here conjunction P, we have and, so we have and Q. And negation of conjunction, we have to write. Negation of conjunction is equivalent from De Morgan's rule to not P or not Q. So we will have not P. So we have A is greater than B is our P. So not P will be, when we have negate A is greater than B, so we will have A is less than or equals B. This is negation of P. And negation of Q is, we have B is greater than C, so negation will be B is less than or equals C. Now we can rewrite our statement. We have to write negation of a statement, so will be not P or not Q. So we have A is less than or equals B, or B is less than or equals C. This is my solution. We have given conditional statement P implies Q. This statement is false. And we have to first find what does this imply about true value of each P and Q. We know that conditional statement is false only when hypothesis is true and conclusion is false. So, because this conditional first statement is false, it means that P is true and Q is false. So we have first answer, and now we have to use this information to find the true value of this statement. We have here conjunction. We know that conjunction is true when both statements are true. So let's check first parenthesis. We have P and Q. Again, we have conjunction in parentheses. And conjunction is true when both statements are true. Because P is true and Q is false, it means this statement is false. So now we don't need to check the second parenthesis because we have conjunction. First statement is false. It means this whole statement is false. So let me write this, that P and Q, and we have in parentheses not P implies Q is false statement. This is my solution. We have to use letters to write argument in symbolic form. What is first argument? Argument consists of set of statements called promises. In some books we can find that this is hypothesis, and another statement called the conclusion. So let's look our example. We have, if I work hard, then I learn lots of money. If I earn lots of money, then I buy a house. Therefore, if I work hard, then I buy a house. So let me put that P will represent simple statement, I work hard. Next we have then, and next simple statement, let's put that this is Q, is I learn lots of money. Next we have if I learn lots of money, so again we have the same statement, simple statement, and next I have when I buy a house. So I will put that R is simple statement, I buy a house. Next we have therefore, and we have if I work hard, I have, this simple statement is P, and I will when I buy a house, I have this is R. So now let's read from the beginning. We have if I work hard, then I learn lots of money. So we have conditional statement because we have here if then. So let me write this. We have P because P represents I work hard, implies I learn lots of money. So this is our Q. Next we will put in next row, again we have word if then. So again we have conditional statement, I learn lots of money. So this is our Q, implies I buy a house. So this is our R. And next we have word therefore. So we have underlined these two statements. First statement is our first promise. Second statement is our second promise. For word therefore we have next, we use 3 dots. And next, this is for symbol therefore, we have if I work hard, then I buy a house. Again, I have if, then. So we have again conditional statement. And I work hard, this represents P. And we have implies I buy a house is R. So this is our conclusion. This is my solution. We have given argument. Let me remind you, argument consists of sets of statements called promises. In some books we have called them hypotheses, and another statement called the conclusion. Conclusion is always after word therefore. So we have, let's read this argument. If I stayed up late at night, then I will be tired in the morning. I am not tired this morning, therefore I did not stay up late last night. So first statement we have if I stayed up late at night, then I will be tired in the morning. So we have conditional statement because we have word if, then. So we will put that first simple statement, we will call this P, is I stayed up late at night. The second simple statement will be, let's put Q, is I will be tired in the morning. Next we have I not tired. So we have statement, simple statement, I will be tired, so this is negation, so we don't have to write another simple statement. Next we have therefore. For therefore we use always 3 dots. And I did not stay up late last night is the statement which we have, only we have negation of P. So now we can rewrite our argument to letters. First we have, like I said, conditional statement. If, then. So we have P implies Q. This is our first promise. Or in some book you can have word hypothesis. And next we have I'm not tired this morning. So this is negation of our Q. So we have not Q. Next we have therefore. So it means we have to underline our promises. We have 2 promises. First and second. And now for word therefore we have to put 3 dots. And next we have I did not stay up late last night. So this is negation of our simple statement P. So we have not P. So this is our conclusion. This is my solution. We have given argument and we have to rewrite this argument in symbolic form. We know that argument consists of set of statements called promises. In some book the promises they called hypothesis, and another statement called the conclusion. So let's see what we have here. We have if we serve chicken, then Skyla will join us for lunch. If Skyla joins us for lunch, then Michael will not join us for lunch. Therefore, if we serve chicken, Michael will not join us for lunch. So let's put that first simple statement will be we serve chicken. So we have conditional statement here because we have if, then. So let's put P as simple statement we serve chicken. Next, then another simple statement will be Skyla will join us for lunch. This is our Q. Skyla will join us for lunch. Next, we have Skyla is join us for lunch, so we have this simple statement, and we have Michael will not join us for lunch. So let's put that our R simple statement is, because we have negation here, so I will put that R is Michael will join us for lunch. Next we have therefore. For therefore we use 3 dots, and we have again conditional statement if we serve chicken. So we have a simple statement Michael will not join us for lunch. So we have this. So let's now write our argument in symbolic form. We have if, then. So we have conditional statement. We serve chicken is our P. Implies Skyla will join us for lunch is our Q. So this is our first premise. So this is our first premise. Or you can call this is our first hypothesis. Next we have again if, then. It means we have conditional statement, and we will write that Skyla joins us for lunch is our Q. implies we have Michael will not join us for lunch. We have that are is Michael will join us for lunch, so we have negation of are. And next we have therefore, so it means we have to underline our two promises. There is a second promise. And for therefore we use 3 dots. And we have conclusion. If we serve chicken, Michael will not join us for lunch. So we have again conditional statement. If something, we have comma, Michael will not join us for lunch. So we have we serve chicken is our P, implies Michael will not join us for lunch, not are. This is our conclusion. This is my solution. We have given argument. I will study if I like mathematics. Either I don't study or I pass mathematics. If I don't graduate, then I didn't pass mathematics. Therefore, if I like mathematics, then I will graduate. So first, let's find simple statements. Because argument consists set of statements called promises or hypothesis, and another statement called the conclusion. Conclusion is always after therefore. So we have promises. I will study if I like mathematics. So our first simple statement, let's put that this is P, is I will study. Second simple statement is Q is I like mathematics. Next, we have either I don't study, we have I will study, so we don't have to write again. I passed mathematics, so let's put that this is our R, is simple statement. I pass mathematics. Next, we have I don't graduate. We have negation because we have don't, so let's put that as is I graduate. And I have I didn't pass mathematics, so we have negation of R. And we have if I like mathematics, simple statement we have. I will graduate, we have. So now we will start from beginning. We have I will study if I like mathematics. So we have conditional statement. We always start if, from if. So we have if I like mathematics, I will study. So I like mathematics is our Q. So we have conditional statement. Q implies I will study. So this is our P. Next we have, this is our first promise. Next we have either I don't study or I pass mathematics. So we have this junction. So I don't study. So this is our negation of for I will study. So we have negation of P. And we have or, because we have or, so this is symbol for or. I pass mathematics is our R. So this is our second premise. Next, we have if again, I don't graduate, then I didn't pass mathematics. So this is conditional statement, we have I don't graduate. We have I graduate. This is our S. So this is negation of S. Then we have, so this is implies I didn't pass mathematics. I pass mathematics is our R. So we have negation of R. This is our third premise. And next we have therefore, so we have to underline our premises. We have therefore, so we have to put 3 dots. And next we have if then. So again we have conditional statement. I like mathematics is our Q. Implies I will graduate. This is our S. So this is our solution. The last row is our conclusion. We have given argument and we have to rewrite our argument in symbolic form. So let's read first. Either I wear a yellow tie or I wear a red hat. I'm wearing a red hat, therefore I'm not wearing a yellow tie. So we have to find the simple statements. We have first simple statement, I wear a yellow tie. So let's put that, this is our P is I wear a yellow tie. Next simple statement will be Q, I wear red hat. Next we have I am wearing red hat, so we have this simple statement and we have therefore I'm not wearing a yellow tie. So we have negation of first simple statement. So now we can rewrite our first statement, either I wear a yellow tie or I wear red hat. We have or, it means we have disjunction. We have P or Q. This is our first premise, hypothesis. And next I have I am wearing red hat. So again we have Q. This is our second premise. Next we have therefore, so we have to underline our premises and we have 3 dots for word therefore. And I have I not wearing yellow tie. So we have negation of first simple statement. So we have not P. This is our conclusion. This is my solution. We have to use truth table to determine whether the argument is valid or invalid. We have given argument in symbolic form. In first row we have first promise. In the second promise. And underline we have conclusion. Now we have to construct a truth table. So to construct a truth table we have to first write how many simple statements we have here. We have P and Q. So we have 2 simple statements. It means we will have 2 to second, so this is 4 rows. Because P can be true or false, Q can be true or false. So we have 4 combination. And what else? When we have true, we will use letter T or 1. When we have false, we will use letter F or 0. I like to use 1 and 0. In some books you can find T, F. Now we have to construct a truth table that shows the true value of each promises and the true value of a conclusion for all combinations of true values of a simple statements. So we have only 2 simple statements. So we have column for P statement, for Q statement. And because we have here not P, so next I will put not P. In next column, we have to write first premise. And first premise is conjunction, not P and Q. Next, we have to write second premise. And this is not P. And in the last column, we have to put conclusion. This is Q. So now, first we have to write all combination of P and Q. P can be true, Q true, P true, Q false, P false, Q false, and P false, and Q true. We have 4 combination. Next, we need to find not P. So we have not 1, so 0, not 1 is 0, not 0, so this is 1 and 1. First premise, like I said, we have conjunction. Conjunction is true only when all simple statements are true. So not P and Q must be true. So let's see, we have first not P and Q is in the second and third column. We have 1 and 0. So this is false. 0 and 0 false. 0 and 1 false. And we have 1 and 1. So this is true. Next we have to write second value, true value for second promise. We have not P, so we can just copy our third column, 0, 0, 1, 1, and conclusion is Q, so we have to copy second column. We have 0, 1, 0, 0, 1. So this is our truth table for this argument. Now we have to check if the conclusion is true in every row of a truth table in which all the promises are true. The argument is valid. So the promises are true only in the 4th row. So we can cross first row because promises are false, second and third. Only we have to look in the 4th row. In this row, promises are true and conclusion is true. It means that our argument is valid. This is my solution. We have given argument in symbolic form. So it means in first row we have first promise. This is our first premise. In the second, we have second promise. And we have conclusion. Next, we have to check how many simple statements we have here. We have P and Q only. It means we will have 2 to second power combinations. So this is 4. So we will have 4 rows. Next, we will use in truth table for true. We can write T or 1, and for false we can use F or 0. I like to use 1 and 0. In some books you can find T and F. So now we have to draw truth table. In first column we will put P, simple statement Q. Next, because we have in first premise not P, so we put negation of P. Next, we have to put first premise. This is not P implies Q. Next, we have second premise. This is P. And in the last column we will put conclusion. This is not Q. So now, first we have to write all combination P and Q. We have to have 4 rows. So it will be true, 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 false, 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 true. And now not P, so not 1, not true. So this is 0, 0, not 0, so will be 1, 1. Next we have conditional statement, and we know that conditional statement is false only when hypothesis is true and conclusion is false. So not P is false, Q is 1. So this is true. We have 0, 0, so this is true. We have now 1 implies 0. True implies false. So this is false. And 1 implies 1. This is true. Next, we have to copy P, because P is the second premise. So this is 1, 1, 0, 0. And Q, conclusion, and conclusion is not Q. So we have not 1, so this is 0, 1. Next, we have not 0, so will be 1. Not 1, so will be 0. Now, we have to check if the conclusion is true in every row of the truth table in which all of the promises are true. So let's see. We have that promises are true in the first and the second row. In third row we can cross because promises are false. And fourth we can cross because one is true, one is false. We have to check only rows where promises are true. This is in first and in the second row. And now we have to check conclusion. When promises are true, we see that conclusion is false, true. Because conclusion is false or true, it means that argument is invalid. So we have This is my solution. We have given argument in symbolic form. Now we have to just write that we have in first row first premise, in other words, hypothesis. This is first premise. In second row we have second premise, and underline we have conclusion. Next we have to write how many simple statements we have here. We have P and Q. It means we will have 2 to second power, so this is 4 rows. 4 combination of simple statements. Next, I will use for true 1 and for false 0. In some books you can have that for true they use T, for false they use F. I like 0 and 1, so I use this. So now you have to build truth table. We have P, Q. Next we have to check if we have negation of simple statement. We have not P, so this is third column, not P. And next, because in first premise we have conjunction and we have statements in parentheses. So first we will find values for P implies Q and not P implies Q. So let's put this in the fourth column. It will be P implies Q, and we have not P implies Q. And now we will put first premise. It is not P implies Q and not P implies Q. And next we have second premise. This is Q, and the last column is conclusion, P. So now first we have to write all combination of P and Q. P can be true, Q true, P true, Q false, P false, Q false, and P false, Q true. Next we have not P. So not 1 will be 0, not 1 will be 0, and not 0, so not false, this is 1, not false, this is 1. Now, in fourth column, we have conditional statement, and we know that conditional statement is false only when true implies false. So let's see, we have 1 implies 1, so this is true, 1 implies 0, true implies false, so this is false, false implies false, this is true, false implies true, this is true. So now we have again conditional statement, not P implies Q. So we have third column and second column. False implies true, so this is true. False implies false, this is true. True implies false, so false. And true implies true, so this is true. Now we have conjunction. So we know that conjunction is true only when both statements, both statements are true. So we have to look in the fourth and fifth columns. So we have 1 and 1, so this is 1, 0 and 1, so this is 0, 1 and 0. So this is 0, 1 and 1, so this is 1. Now we have to copy Q. Our second premise is Q. So 1, 0, 0, 1 we have. And conclusion is P. So we have 1, 1, 0, 0. Now we have our truth table. We have to now look on our promises and conclusion. We know if the conclusion is true in every row of the truth table in which all the promises are true. So we have promises true in the first row and conclusion is true, but in the fourth row we have promises true and conclusion is false. We got in fourth row that conclusion is false and both promises are true. So it means that argument is invalid. Why? Because if the conclusion is false in any row in which all promises are true, the argument is invalid. This is my solution. We have given argument in symbolic form. First row we have first promise. This is our first premise. In the second we have second promise, and underline we have conclusion. Now we have to write how many simple statements we have here. We have P, Q and R. It means we have 2 to third power combinations. So this is 8 rows we have to have. And for true, I will use 1, and for false, I will use 0. In some book you can have T for true and F for false. I like use 1 and 0. So now we have to write all this combination. We need to have 8 rows. So we have P, Q and R. Next, we have to put negation of simple statement. We have not R only. And next, first premise is conditional statement. So I will put first this statement in parentheses. So we have P implies not R. And the second parenthesis is Q and R. And now it will be very easy to find the value for first premise. First premise, this is P implies not R, implies, and in parentheses we have Q and R. Now we will have second premise. This is R and P, and in the last column we have conclusion. This is P or Q. So now we have to find 8 combination. So we have 1, 1, 1, 1, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, and we have 0, 0, 0. We need to have in every column for P 4 truths and 4 false. For Q the same. We have to have 4 truths and 4 false. The same for R. Now you will have to write not R, so we have to look in the third column. Not 1, so will be not true, so this is false. Not false, so will be 1, 1, 0, 0, 0, 1, 1. Next we have conditional statement, and we know that conditional statement is false only when true implies false. So we have to look first in first column and in the fourth. So we have 1 implies false, so this is false. 1 implies 1, so this is 1, 1. 1 implies false, so this is false. 0 implies 0, so this is true, true. 0 implies true, so this is true. And 0 implies true, so this is 1. Next, we have conjunction, and conjunction is true only when both statements are true. We have Q and R simple statements, so we have 1 and 1, so this is 1, 1, 0, 0, 0, 0, 0, 0. And now we have to look to fifth and sixth column, and we have again conditional statement, and we know that conditional statement is false only when true implies false. We have 0, 1, so this is true. 1, 1, so this is true. 1 implies 0, so this is false. True. 1 implies 0, so this is false, 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 and false. Now we have again conjunction statement, R and P. Conjunction is true only when both statements are true. So we have R and P, 1 and 1. So this is true, false, false, true, false, 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 and false. And we have disjunction statement, P or Q is false only when both statements are false. So we have 1 and 1, so this is true, 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 true. 0 or 0, so this is false, true, false. And now we have to check our promises and conclusion. We have true promises in the first row, and conclusion is true. We have true promises in fourth row, and conclusion is true. So it means that our argument is valid because for true promises we have true conclusion. So let me write this. The argument is valid. This is my solution. We have to use truth table to determine whether the argument is valid or invalid. First, we have to write our argument in symbolic form. So we have Gabi will not go on the cruise if she buys a house. Gabi went on the cruise, therefore Gabi did not buy a house. So let's put that Gabi will not go on the cruise will be our first simple statement because we have not. So I will put that this is not Q. So let me circle this with. This is our first simple statement and will be not Q because we have will not negation of Q. I can write that Q is Gabi will go on the cruise. Next we have simple statement she buys a house. This will be our P statement. And next we have Gabi went on the cruise because Gabi will not go on the cruise was not Q. So Gabi went on the cruise will be our Q simple statement. And we have therefore Gabi did not buy a house because she buys a house is our P. So she did not buy a house will be our not P. So now we can rewrite our argument in symbolic form. We have first conditional statement we have because we have word if. If she buys a house, Gabi will not go on the cruise. So we have to start from this part. If she buys a house. So we have P implies Gabi will not go on the cruise, not Q. This is our first premise. Next we have Gabi went on the cruise. So this is our second premise. And we have word therefore, so we will underline our premises and we will put 3 dots for word therefore. And we have Gabi did not buy a house. This is not P. We have our argument in symbolic form. Now we have only P and Q simple statements. So we will have 2 to second power. It means we will have 4 rows, 4 combinations because P can be true or false, Q can be true or false. I use for true 1 and for false 0. In some books you can find T for true and for false F. I like 1 0. That's why I use this symbol. So next we have to build truth table. We have simple statement P, Q, and we have negation of Q. So next will be negation of Q. First premise we will put next. This is conditional statement. P implies not Q. And the second premise is next. This is Q. And our conclusion, I forgot to write. This is conclusion. This is not P. So we have true, 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 false, false, true, false, false. We have 2 simple statements. It means we have to have 4 rows. We need to have for P true, 2 truths and 2 false. And the same for Q. Next we have to write not Q. So we have to look in the second column, not 1, so it will be 0, not 0, so it will be 1, 0, 1. We have conditional statement, and we know that conditional statement is false only when true implies false. So we have P and not Q. So we have true implies false, so this is false. 1 implies 1, so it's true. 0 implies 0, so this is 1. 0 implies 1, so this is 1. Next, we have to copy Q, because second premise is Q statement. Simple statement, 1, 0, 1, 0. And we have negation of P. So not 1 will be 0, not 1 will be 0, not 0, so will be 1 and 1. So we have our truth table. Now we have to check our premises. We have true promises in the third row, and conclusion is also true. Because conclusion is true, promises are true, it means that our argument is valid. If conclusion is false, in any row in which all of the premises are true, the argument is invalid. In this example, premises are true and conclusion is true. So this is valid argument. This is my solution. We have to use standard forms to determine the validity of an argument. We have argument either I wear a red dress or I wear pink skirt, either I wear a black hat or I do not wear pink skirt, therefore I wear a red dress or I wear a black hat. So first we have to rewrite our argument in symbolic form. So let's put that first simple statement we have here is I wear a red dress will be our P is I wear a red dress. Let Q is I wear pink skirt. Next, we have I wear a black hat. So this is another simple statement. Let's put that this is R. And next, we have I do not wear pink skirt. So we have negation of Q statement, and I wear a red dress again, and I wear a black hat. So we have three simple statements. Now we have to rewrite our argument in symbolic form. So we have either I wear a red dress, and we have word or. Or is for disjunction. So we will have I wear a red dress, so this is our P. We have or I wear a pink skirt, this is our Q. This is our first premise. Next, we have either I wear a black hat, so this is our R, or again we have, so it means we have disjunction. I do not wear pink skirt. So we have negation of Q. So this is our second premise. Next, we have therefore. It means we have to underline our premises, and we have word therefore. It stands for 3 dots, and we have I wear a red dress, again or. It means we have disjunction statement, and we have I wear a red dress, so this is our P, or I wear a black hat. Black hat, this is our R. So we have P or R is our conclusion. This symbolic form matches the standard form known as resolution. So our argument is valid. This is my solution. We have to use standard form to determine the validity of argument. So first we have to write the argument in symbolic form. We have here argument: if I finish my homework, I may go to the park. I did not finish my homework, therefore I cannot go to the park. So first we have to find simple statements. Let's put that P is simple statement: I finish my homework. Next, we will put that Q is I may go to the park. Next, we have I didn't finish my homework, so we have negation of P. And we have I cannot go to park. This is negation of Q. So now we can rewrite our argument in symbolic form. We have if I finish my homework, I may go to the park. So we have here conditional statement. P implies Q. This is our first premise. Next, we have I did not finish my homework, so we have negation of P. And because we have therefore, so negation of P, this is our second premise. And now we have to underline our premises, and we have 3 dots, various state for therefore, and we have I cannot go to the park. So this is negation of Q. We see that this symbolic form matches the standard form known as fallacy of the inverse. This is standard form of invalid argument. So let me write this, that this is fallacy of inverse. and it means that our argument is not valid. Invalid. This is my solution. We have given argument and we have to determine the validity of this argument. We have to use standard forms. So let's read this example. We have I can't buy a car. I can buy a car, or at least I can dream about it. Therefore, I can dream about it. So let's first find simple statements. We will put that I can't buy a car. We have first. So let's put that I can buy a car will be our P is I can buy a car. Next, we have or at least I can dream about it. So this is our second simple statement. Let's put that this is Q is I can dream about it. So now, what we have? I can dream about it. Okay, therefore, so now we can rewrite our argument in symbolic form. We have first, I can't buy a car. So we have negation of P. Next, we have I can buy a car, or at least I can dream about it. So we have or, it means we have here this junction. So we have P or Q, and we have therefore. So this is our first premise, not P, let's write. Next, this junction P or Q is our second premise. And because we have therefore, so it means next we have conclusion for word therefore. We put 3 dots and we have conclusion I can dream about it. This is our Q. This is conclusion, of course. We can change the order and we can put now first that we have this junction P or Q. The second premise we can put first, and next we have not P, and we have conclusion Q. So now we see that our symbolic form matches the standard form known as disjunction syllogism, the standard form of valid argument. So let's write this. We have disjunctive syllogism. It means that our argument is valid. This is my solution. We have given argument and we have to use standard forms to determine the validity of this argument. Let's read this first. If I get the job and work hard, then I will get promoted. If I get promoted, then I will be happy. I will not be happy. Therefore, either I will not get the job or will not work hard. First, we have to find simple statements. We have if, then. So we have here conditional statement. First simple statement will be I get the job, and because we have and, it means we have here conjunction statement too. So let's put that P is first simple statement and it will be I get the job. Next, let's put that Q is I work hard. Next we have I will get promoted. So let's put that R is I will get promoted. Next we have if I get promoted, so it's the same, then I will be happy. So we will put that S is I will be happy. Next, we have I will not be happy, so we have negation of S. Therefore, either I will not get the job, so we have P-I get the job, so we will have negation of P, and or will not work hard, so we have negation of Q. So we have all simple statements. Now we can rewrite our argument in symbolic form. So we have first conditional statement, if something then, so we have conditional statement and we have here and. So inside conditional statement we have conjunction statement. So first we will have I will get the job, so this is P, and work hard, this is Q. And next we have that this imply I will get promoted, this is our R. Next we have again if, it means we have conditional statement, I get promoted, so this is our R. Then I will be happy, happy is our S, so we have R implies S. Next we have I will not be happy, so this is negation of S. So this is our first premise. Let's write this. This is our first premise. This is our second. And third. Next, we have word therefore. So it means that we have next conclusion. So we can underline our premises and we have to put 3 dots. They are stand for therefore. And we have either I will not get the job, or we have, it means we have disjunction statement here. I will not get the job, so this is negation of P. We have or I will not work hard, so this is negation of Q. So next we have to look at our premises first. We see that our second premise and our third premise is standard form known as modus tollens. Let me write this, that second and third premise matches the standard form known as modus tollens. So now we can rewrite our symbolic form. First premise we have to copy. We have P and Q imply R, and we will substitute the second and third premise by negation of R. So now we have conclusion not P or not Q. This is our conclusion. Next, we can rewrite our conclusion from De Morgan's law that this is equivalent to, let me write this, that not P or not Q is equivalent to not P and Q. This is negation of conjunction. This is from De Morgan's law. So now we can rewrite our symbolic form, and we have P and Q imply R, not R. This is our second premise. And our conclusion, we can rewrite that this is not P and Q. Now we see that this symbolic form matches again the standard form known as modus tollens. So this is, we can write again modus tollens. This symbolic form matches the standard form known as modus tollens. So it means that our argument is valid. Let me remind you, maybe here I can put this standard form. When we have A implies B, this is first premise, the second is not B, so the conclusion is not A. We have exactly the same symbolic form. Our A is, let me write this here, A is equal P and Q, and B is our R. So we have exactly the same form here. That's why our argument is valid. This is my solution. We have to use standard forms to determine the validity of an argument. So let's first find the simple statements, because we have to rewrite our argument to symbolic form. So we have, if I study mathematics, then I will make a lot of money. We have conditional statement here. First simple statement will be I study mathematics. Let's put that this is our P. Next we have I will make a lot of money. Let's put that this is our Q. Next we have again if, it means we have conditional statement. I study archaeology, so this is our R, simple statement. We have then, I will travel a lot. So let's put that this is our S, simple statement. Next, again, we have here conditional statement. If I make a lot of money, so again we have Q, or again we have here travel a lot, so this is our S. Then I will not be disappointed. So let's put that I am disappointed will be our D statement. And we have I did not study mathematics, so we have negation of P. And I did not study archaeology, so this is our negation of R. So now we can rewrite our argument to symbolic form. We have if, so we have conditional statement, like I said before. We have P implies Q. We have then I will make a lot of money. Next we have if, so we have again conditional statement. This was our first premise. Let's write this. Next we have R. I study archaeology, then I will travel a lot. R implies S. So this is our second premise. Next, again, we have conditional statement. If I make a lot of money, and we have or, so we have this junction here. I make a lot of money, so this is our Q, and we have or, travel a lot, so this is our S, and we have to put this in parentheses. This imply I will not be disappointment. I am disappointment is our D, so negation will be not D. This is our third premise. Next we have therefore. It means next will be conclusion. We can underline our premises. For therefore we will put 3 dots. And we have conclusion. If, it means we have again conditional statement. We have I am disappointment, so this is our D, implies, and we have I did not study mathematics, so we have negation of P, and because we have and, so in parentheses we will have conjunction statement. I did not study archaeology, so we have and negation of R. This is our conclusion. Now we can rewrite our third premise. This is equivalent to, let me copy this. We have Q or S imply not D. This is equivalent to Q implies not D, and S implies not D. So we can copy first and second premise, and the third we can rewrite to this form. So let's do this. We have P implies Q, R implies S, and now we will have Q implies not D, and S implies not D. So now we have our conclusion. D implies not P and not R. Now we can use law of syllogism because we have here P implies Q and Q implies not D, and we have R implies S and S implies not D. So we can rewrite our symbolic form now to P implies not D, first premise and third, and we have R implies not D, and we have conclusion D implies not P and not R. Now we know that conditional and its contrapositive statements are equivalent statements. So we can rewrite that P implies not D is equivalent to not D implies not P. I just use contrapositive here, and we have R implies not D. So this is equivalent to not D implies not R. This is contrapositive. So we see that we have not D. So it will be D implies not P. So we can rewrite our promises. P implies not D. It will be D implies not P. And we have R implies not D. This is equivalent. Not D give us D implies not R. And our conclusion is D implies not P and not R. We see that we have here D implies not P and D implies not R. This is equivalent to D implies not P and not R from the table of logical equivalence. So we show that our argument is valid. This is my solution. Use all of the promises to determine a valid conclusion for the given argument. First premise is not P or Q. So we have this junction statement. This is equivalent to conditional statement P implies Q. Let me write this. We have not P or Q. This is equivalent to P implies Q. So we can rewrite first promise, and we will have now P implies Q, and second we can copy Q implies not R, and we have S implies R, S or H. So now we have here law of syllogism. We have P implies Q and Q implies not R. So for the first and second promise we can use law of syllogism. And now we will have for the first and second promises, we will have that P implies not R, and third and fourth promise we have to copy. We have S implies R, and we have S or H. So now we can use contrapositive and rewrite that. Let's put this here. S we have implies R. So this is equivalent to not R implies not S. So we will have to copy first premise. We have P implies not R, and the second we will substitute that equivalent form not R implies not S, and the third promise we will copy S or H. So now we can use again law of syllogism. We have P implies not R implies not S. So these two promises we will substitute by P implies not S from law of syllogism. Again, and the third we have to copy S or H. So now we know that we can rewrite disjunction to equivalent form to conditional form. So let me remind you this formula. When we have that A implies B, this is equivalent to not A or B. In our example, we have that S is not A and B is H. So we will have to change this to conditional statement, and we will have that S or H is equivalent to not S implies H. I just used this formula. So now we can rewrite our second premise. First we will copy P implies not S, and the second is equivalent to not S implies H. So we see that we have here again law of syllogism. This is equal to P implies H. P implies not S implies H, so P implies H. This is our valid conclusion. This is my solution. Use all of the promises to determine a valid conclusion for the given argument. So first we have to rewrite our argument to symbolic form. So we have to find simple statements. Let's put that she buys the house will be our P. Next simple statement will be she will need a loan. So this is our Q. Next we have she does not need a loan. So we have negation of Q, or she will make monthly payment. So let's put that this is our R. Is she will make monthly payments, and she buys the house. So this is our P. So now we can rewrite our promises we have if. It means we have conditional statement. So she buys the house is our P, implies she will need a loan. This is our Q. First promise. Next we have she does not need a loan or she will make a monthly payment. So because we have or, it means we have disjunction. She does not need a loan, so we have negation of Q, or she will make monthly payments. So this is our R. Next we have she buys the house. This is our P. So we have three promises. We have to find valid conclusion. We have not Q or R. This is equivalent to Q implies R. So now we can rewrite our promises and we will have P implies Q. Instead of not Q or R, we will put Q implies R. We have P. And now we see that to first and second promises we can use law of syllogism. This will be P implies Q, Q implies R. It means that P implies R and we have to copy P. So we see now that we have here modus ponens. Standard form of valid argument, modus ponens. When we have P implies R, first promise, and we have promise P, conclusion is R. So we have that our conclusion R is she will make monthly payments. So the answer is she will make monthly payments. This is my solution.